Welcome to this explainer. Have you ever looked at a massive industrial plant with its towering pressure vessels and those endless runs of piping and wondered what really holds the whole shebang together? It's super tempting to just look at the massive steel bolts and the thick metal plates. But the real secret? It's completely invisible to the naked eye. Today, we're going to explore how the unseen, microscopic atomic structures of metals absolutely dictate the real-world behavior of those massive engineering projects. Because mastering material science, well, it starts by looking at the very, very small.
So, here's our quick roadmap for today. We'll start with an intro to metal structures, compare BCC and FCC lattices, look at strength versus toughness, solve a fun magnetism mystery, talk about carbon versus stainless steel, and wrap up with an awesome kitchen hammer experiment.
All right, Section 1. Intro to Metal Structures.
Okay, let's dive right into this. When you're engineering a huge plant, the sheer variety of materials can honestly feel a bit overwhelming. But we can simplify this vast world of metallurgy by focusing on a really handy dual-track framework. In the engineering world, you're primarily going to encounter two foundational metal structures, ferrite and austenite. Now, the names might sound a bit academic, but almost every single piece of metal equipment you work with in a plant is going to predominantly feature one of these two structures, or a mix of both. Understanding the difference between ferrite and austenite is literally the foundational secret to predicting exactly how a material is going to behave under intense pressure and extreme temperatures.
Moving on to Section 2, BCC versus FCC lattices.
To truly get a grip on these materials, we need to zoom way, way down to the atomic level. And what's really fascinating here is the precise geometry of ferrite. This is what we call a body-centered cubic structure, or BCC for short. I want you to imagine a tightly packed cube of atoms. In a BCC structure, you've got atoms sitting at all the corners of the cube. But the absolute most important feature is right in the middle. There's a solid, completely filled center containing an iron atom. It is packed, it's dense, and it's solid straight through its core.
Now contrast that with austenite, which uses a face-centered cubic structure, or FCC. At first glance, yeah, it's still a cube, but look a little closer. The atoms sit on the faces of the cube, leaving the absolute center of the lattice completely empty. It's essentially a microscopic box with a hollow core.
So, putting them side by side, we have ferrite with the solid iron center on the left, and austenite with the hollow, empty center on the right. I really want you to burn this microscopic geometric difference right into your memory. This single distinction, a solid center versus an empty center, is the secret master key. It's the key that dictates almost all of the real-world macroscopic behavior of these metals.
Section 3. Strength versus toughness.
Let's see how that master key actually unlocks physical properties, specifically how these metals respond to intense physical stress and extreme temperatures. We have a chart here that brilliantly illustrates exactly what happens when things get cold. If you follow the line representing our BCC ferrite structures, you'll see that at high temperatures it handles impact just fine. But as the temperature drops, the impact energy just plummets. It becomes completely brittle and can actually shatter. Now check out the data for our FCC austenite metals. Even as the temperature drops well below freezing, it maintains high impact energy. It stays incredibly tough, even in the most freezing environments.
So why exactly does this happen? Well, it all goes right back to the center of those cubes. The solid core of the ferrite BCC structure makes it highly resistant to bending, which grants it fantastic overall strength. Actually, think of it like a solid brick. But because it's so rigid, it can't absorb sudden shocks well, giving it lower toughness. Austenite, on the other hand, has that empty space in the middle of its FCC lattice. That empty space literally acts like a microscopic shock absorber. When you hit it, the lattice actually has room to flex. This results in slightly lower overall strength, for sure, but incredibly high toughness, preventing it from shattering when it gets cold.
All right, Section 4. The magnetism mystery.
Now, let's step out of the heavy engineering diagrams for a second and move into a really fun practical property that completely separates these two structures in everyday life. Have you ever wondered why a magnet sticks to some metal objects in your house, but just slides right off others? It's a mystery we've all experienced at some point, and the answer is hiding right in that microscopic geometry we just talked about.
Here's the deal. For a metal to be magnetic, the magnetic pole needs a continuous, unbroken path of atoms to flow through. In ferrite's BCC structure, that solid iron atom sitting right dead center creates a continuous, unbroken connection. Therefore, ferrite is magnetic.
But over in Austenite's FCC structure, that empty space in the center physically breaks the connection. The chain is broken, which means austenite is non-magnetic. Section 5. Carbon versus stainless steel. Let's bring this back to the plant floor and build up our understanding of real-world engineering materials. How do we actually order these things when designing a massive pressure vessel? Well, in the real world of industrial engineering, when a process engineer specifies carbon steel, what you're essentially getting is our Ferrite structure. It's strong, it's magnetic, but remember, it can be brittle in the cold. Conversely, when you specify 300 series stainless steel, like 304 or 316, you're getting our Austenite structure. It's a tiny bit lower in absolute strength, but it features incredibly high toughness. It thrives in freezing temperatures, it has fantastic anti-corrosion properties, and yep, it is totally non-magnetic.
And finally, Section 6, the hammer experiment.
Okay, I absolutely love this part. I want to introduce a highly memorable, hands-on kitchen experiment to ground all this abstract atomic science into an everyday reality you can actually see and hear. Try this out later. Grab a magnet and find a high-quality 300 series stainless steel pot or spoon in your kitchen. First, put the magnet on it. It won't stick, right? That's because it's austenite. Now, step 2, and maybe do this outside. Take a heavy hammer and smash that metal until it dents. Step 3, put the magnet exactly where you dented it. Suddenly, it sticks. No way, right? Finally, step 4. If you were to heat that dented metal up until it's glowing red hot and then rapidly quench it in cold water, the magnet would fall right off again.
So the absolutely crucial point here is understanding why this happens. When you smash that pot with the hammer, the intense physical force literally compressed the empty space inside the FCC austenite lattice. By squishing the atoms together, you forced them into a tighter partial BCC structure. You effectively created a continuous path for the magnetism to flow. Then, when you heated it up to extreme temperatures and rapidly cooled it, a process called solution annealing in the industry, you gave the atoms enough energy to relax back into their natural, spacious FCC structure, expanding the empty space, breaking the magnetic connection, and dropping the magnet.
And that pretty much wraps up our explainer. Mastering material science isn't just about memorizing data sheets. It's about understanding how the unseen, microscopic atomic world directly controls massive, real-world engineering projects. So the next time you see a giant stainless steel tank, or honestly even just a spoon in your kitchen, I want you to think about those tiny, hollow cubes keeping it tough and strong. What will you discover when you look closer? Thank you so much for joining us, and keep exploring.